So we are ready for the last talk of the morning by Mark Kessebohmer about spectral dimensions of Krein-Feller operators in higher dimensions. Please.
Infinitesimal generators of Feller processes, so diffusion processes, and depending on the underlying measures, they are gap diffusions and widely studied and quite interesting. Solving the problem of describing the spectrum, it turned out that dynamical methods like thermodynamic formalism, depending on the measures you are looking at, played a crucial role. But in this talk, I want to show you that you can do with less dynamical methods and say more about the general problem, but in less generality. So we don't attack the complete problem of finding the spectral asymptotic, but we will look for the spectral exponent, and we will solve that the lim sup of this exponent exists, and we identify it with a notion of something which is similar to the notion of topological pressure. Okay, I start with some motivation to the theory of Krein-Feller operators. Very easily in one dimension on a compact interval 0, 1. It models the string on the interval 0, 1. That is, you have to solve the differential equation second derivative of f is equal to a constant times f, so the eigenfunctions of the Laplace operator solves the problem with boundary condition 0 of a vibrating string, and then you know the spectrum is discrete. You want to find all the eigenvalues, and you are in particular interested in the asymptotics of these eigenvalues. This is denoted here by ft. I should have called this n, because later on it's called n. And of course, this is 1 over pi square root of t. So in this particular situation, we are fine. Now, if you put some mass on the string, the next slide, this is called rho, some density function rho, which is depicted here with this dark line. Then you can try to solve the same problem. It turns out that you have to do a different kind of differentiation with respect to the measure nu, which is easily possible, and you ask the same question. So the question now is, if we change the measure in this way, what kind of asymptotic can we expect? And the outcome from Krein is, for any probability distribution or any finite distribution, the result is known. It's almost the same, only there is a nice interesting factor. You take the square root of rho and integrate this with respect to the Lebesgue measure on 0, 1, and this gives you the precise asymptotic. Also in this situation, we see that the exponent here is 1/2, and I will call this number the spectral dimension of the measure nu, or of this problem. Now, it turns out that for all measures which have an absolutely continuous part in dimension 1, nothing more will happen. We will see that later. And the interesting question is, what happens if you have a purely singular measure? So if you have instead of d nu, we take any other singular measure with respect to Lebesgue, what can we say about this asymptotic, and what can we say, and that's what I'm focusing on, can we say about this exponent of divergence of the spectrum? Yeah.
Can you see what partial nu or partial lambda means?
We will give a definition in RD in a weak sense, and then it becomes clear. But actually, for one-dimensional case, you can also give a strong definition as a Radon-Nikodym derivative with respect to the density lambda of the function f. All right, so this yellow bit will be called then the Krein-Feller operator, and we define this in the next slide, hopefully. Or maybe some people who are not so happy with the physical motivation are more happy with hyperbolic geometry and some compact Riemann surface. You have the Laplace-Beltrami operator on it. We know it has a discrete spectrum, and then we want to know the spectral asymptotics, like here. And this has been solved a long time ago, and you use ideas maybe of Seelberg's zeta function and the trace formula. So you have a formula. On the one hand side, you have the spectral information. On the other side, you have geometric information, like the length of closed geodesics. And we want to mimic this. We want a formalism which has on the one side the geometric and measure theoretical information. So we have something combined, the geometry and the geometry of this measure. And on the other side, we want to get out this exponent. So that's the overall aim. And what I'm saying, what I mean with we are not attacking the whole problem is we are not, actually there's no way to think that you will always find such an asymptotic. Normally there is none. If you are lucky, you may find two constants, that the quotient is bounded away from 0 and infinity. But in most cases, there's no asymptotic at all. But in any case, you can try to find this exponent, and that's what we are doing. So this is a crash course, because for this weak formulation, we need some Sobolev spaces. I restrict to finite measures on the unit cube in RD. Don't pay too much attention on the boundaries. You can do this with closed cubes, open cubes, what you like. Then the underlying Hilbert space is the L2 space with the underlying measure nu. So very important for the whole talks, this nu is fixed once and for all. Then we have two Sobolev spaces. One is indexed with an n, which stands for Neumann. That's a closure of the C infinity functions, which are uniformly bounded on the interior of Q, and hence you can think of these as continuous functions on the closure of Q. And you take the closure of this set of functions with respect to the usual norm of Sobolev spaces with respect to lambda. So this is all with respect to lambda. And you can do the same thing with compactly supported sets, and then you get the Dirichlet boundary condition. And I denote this by h to the d. And the norm, this will be important, is given by the usual Dirichlet norm. So you take the gradient and takes a multiply these are real valued functions and evaluate the integral. And the idea is, like in the weak formulation in R, to define the second derivative in a weak sense. And for this, we need to embed, because I want to do this not with respect to Lebesgue, but with respect to the measure nu. So we have to embed the set of functions hn and hd into L2 nu, and then define the form as the first derivative, as we done here. So that's the aim. For this, we need this embedding. This is the first crucial point. So of course, by identity, you can include the continued infinite differentiable functions into LT nu. I call this iota. And this is a continuous embedding if you find a constant k, such as this inequality holds. And that is the first obstacle we have to take care of. And this is, in general, not possible. In fact, you need a condition on the measure nu, which is very handy. It has to do with fractal geometry. It is given by Hulao Ngai in 2006. It relies on deep results by Maziar, 85 and probably earlier. And for that, we need to look at the following quotient. You look at the least speed. The measure nu decreases on an exponential rate on a dyadic. That doesn't play a role. So you can think of this as balls with the center in the unit cube divided by log of the radius, or minus, and then takes the largest possible value and takes the limit as lim_inf as n goes to infinity. This number is called the infinity dimension of nu. And we do have this compact, we do have a continuous embedding if this number is greater than d minus 2. So this is a necessary condition to attack the problem of Klein-Fell operators in RD. For an arbitrary measure nu, this is only possible if d nu infinity is greater than d minus 2. If it's less, then it's not even continuous, and then you can forget about defining a weak second derivative in this way. The only part left off is when it's equal to d minus 2, and I'll give examples where you can have all kinds of behaviors. All right. So the problem still is, so we want to embed the differentiable functions into L2 nu, and then we want to define a form which is given by the product, so the scalar product in HDN of these functions. And this is not well defined if the function is not injective. But that is not really a problem, because if it's not injective, the embedding iota, and think of the measure nu has some gaps, to say on the interval you have some gaps, then you can change the function in the Lebesgue sense arbitrary, and you don't see the difference in L2 nu, and you just take the complement, the orthogonal complement in this set, restricted to HD or HN, that's why I made this notation, and then restricted to this set, which I push forward, or push into the map into L2 nu via iota, is then the domain of this nice differential form. And this gives us now the chance to define an operator, a self-adjoint operator, which will be the Klein-Fell operator with respect to nu in dimension R. So what you need to observe that this set of functions which you allow, so the Sobolev space, is densely defined. So on this set of functions, the domain of this form, you need that the domain inside L2 is dense. You can check this easily. It's well defined. This is true because we have this problem of non-injectivity just factored out. And the form is closed. That means with respect to this new inner product, which is the inner product of L2 nu, and the form, this should be a Hilbert space, and you check this also easily. Now the good thing is the condition that this embedding is continuous is not only true, it's also true that this embedding is compact. And now we are in play. So we have a form defined on a Hilbert space densely, which is compact. And this gives rise then to the definition of the Laplacian as a unique, for a given function f in the domain, you define the Laplace operator or the Klein-Fell operator of f as a function h, such that this equality holds for all g in the domain of the form. So the whole problem now depends only on the form and the good properties of density definedness and compact embedding. And because we are in the situation that the embedding is compact, this proves that this operator is compact. So we find a sequence, an orthonormal basis of eigenfunctions, and not counting the multiplicity, we denote in increasing order the eigenvalues by lambda n. With respect to these two forms, one was with the set of functions which have arbitrary values on the boundary, the Neumann problem or the Dirichlet problem, and I distinct this with the dn. If I was just talking about dimension 1, then the difference is very small, but in dimension d, I'm not so sure at the moment. So we keep to this dn business, and now the idea is you can define eigenfunctions with respect to the operator or just in terms of the form. So actually, you don't need really the operator to talk about the eigenfunctions. You just need the form, and then you call something an eigenfunction with eigenvalue lambda if this equality holds for all g in the domain of the form. So everything plays only on the set of differentiable functions. And then the dn will be the counting function, so the number of eigenvalues less than x. And now we define the upper and lower spectral dimension with respect to E, or the operator, or just with respect to the measure nu, as the lim sub of the exponential growth rate, or the lim inf of the exponential growth rate of these counting function. So we forget about asymptotics, we are just looking at the exponent. And the first question, are there examples where these are different? And they are sometimes different. So to expect in general that the asymptotic holds is far from the reality. So how is this connected to the question of, can you hear the shape of a drum? Well, you need this question if you want to apply for a trumpet with your money. And well, it means what we can try to do is connect these numbers as upper bar as lower bar with some geometric information. And we can answer this partially positive and partially negative. Depends on the dimension, actually. So we come back to that question. So now coming back to earlier results on this problem. We had this with an absolutely continuous measure. Now we have a mixture. We have an absolutely continuous part, and which is non-trivial. So it's the rho so this measure is not zero, and some singular part eta. This eta doesn't play a role in the asymptotics. The spectral value will be 1/2, and you can even find the correct term here. It's the same as if you have no eta there. So the interesting parts come if you look at measures which are purely singular. So which was the first result which I found was Hang and Uno in 1959. They just looked at the 1/3 Cantor set, and they could prove that these two notions coincide, they exist, and they proved it's log2 over log3 plus log2 for the 1/3 Cantor set, half-half probability on each side. And it turns out that this is equal to the Hausdorff dimension of nu divided by the Hausdorff dimension of nu plus 1. So there was this guess, this is closely connected to the notion of Hausdorff dimension. And I don't know, this Weil-Berry conjecture from this older than 59. So about the second order of the classical problem of the Laplace operator, there was a guess that the second order term depends on the Hausdorff dimension of the boundary. And then it was shown for a simple example, it depends on the box counting or Minkowski dimension of the boundary. And one outcome here will be that the notion of Hausdorff dimension is not really connected to it. It's really the box counting which plays a role here. So this was 59, then 85. A paper hard to find. This was solved with dynamical methods and other tricks for self-similar measures with open set condition. We have a probability vector P1 to Pn and some contractions R1 to Rn. Then you find, and they also proved the asymptotics, at least in the weak sense. You find the dimension exists for dimension d = 1, and is given by the unique solution of this easy formula. And Solomjak-Verbitsky proved in 93 the precise asymptotic for this particular case. Neymark-Solomjak did the same for higher dimensions with some extra conditions, and these extra conditions turn out to be just these, that the infinity dimension must be greater than d-2. And the same was done by Triebel in 1997 for Alphus regular measures. Actually, the first example was Alphus regular. He proved if nu is Alphus regular, and alpha, it's the same condition, is greater than d-2, then the spectral dimension exists and is given by this nice formula. And this means in particular, which is a bit surprising, that for d = 2, the outcome is always 1. And then in the years 2000s, Ngai and co-authors proved it for every kind of special other measure and used typically dynamical methods to prove similar results. For example, self-similar measures with exact overlap. They can do, they have some matrices, use spectral gap tricks, or for graph-directed systems with open set condition and with exact overlap and so on. So for each example, you need a new proof. So what are the methods normally used? They use some green functions. They use trace formulas. Then they use the self-similarity to reduce a renewal equation. And then if you have spectral gaps, you can, or use Tauberian theorems, you have some chance to get an asymptotic. And if you have asymptotics, you get the right exponent. And then at certain points, I always say, into here you need the min-max principle. Look at Hilbert Courant. There it is written down somewhere. And actually, I started getting interested in this problem because I wanted to look up the min-max principle. I couldn't find it in Hilbert Courant. And all these authors go back to Hilbert Courant. And it's actually a very simple observation. And most of you probably know it. If you have an operator given by a form, or you can define a form if you have an operator, of course, and you know it has a discrete spectrum, then you immediately get that the i's eigenvalue is given by the supremum over all quotients of this form, where you take the supremum over all functions in G, and G is an I-dimensional subspace of the domain of the form. And then you take the infimum over all, and this gives you the order of all eigenfunctions, because the space is spanned by the eigenfunctions. It's pretty easy to prove. Here's a little add-on. If you take, instead of the DOM, you take the whole Sobolev space, it doesn't make a difference, because it's just the kernel, which I divided out, and there the denominator is infinity, so you would get rid of these automatically. So the whole problem in the min-max principle now reduces to looking at I-dimensional subspaces of the Sobolev space. Forget everything else you heard so far. If you are able to quantify this expression, then you are able to solve the problem without the heavy machinery. So let me go back. So the idea is, get rid of the first part, use only the min-max principle and counting arguments with some entropy-like notions. So this is a bit messy because I wanted to show you that this counting argument has nothing to do with the problem I showed you before. So now we are coming to a point where we look at arbitrary set functions on the set of all dyadic subcubes of our starting cube. This is called D, the script D. And you have a monotone set function. Pi j, capital Pi j is a J partition, meaning it's a partition in cubes. And you throw away those where J is 0. And you take an arbitrary partition P in the J partitions, and you look for the largest value of J of some of the elements, and this should be less than 1 over x, and you look for the smallest cardinality you can realize. So these are cubes, you have some, and from J you could think of a measure, okay? So you subdivide it and you get smaller, but you don't do that too often because the aim is just to be smaller than 1 over x, and then you stop. And this gives you some finite number. And then we define the upper and lower J partition entropy, that's how we called it, as the growth rate of this cardinality. So it's the first part for the upper bound. And now if you have such a function, and you can solve this problem with these functions. So here we have a kind of Poincaré inequality with respect to the L2 norm of nu. And we find such an decreasing function J, such as this is true, then the growth rate we defined on the slide before gives you the upper bound for the upper spectral dimension and an upper bound for the lower spectral dimension. So sorry, this has nothing to do with spectral dimension. Here we have the connection via this inequality, and this gives you the, and what you need for the proof of this is just the min-max principle. You look at the functions which are, so you take one of these partitions, just a very brief proof. You go to one of these partitions, P, what is it called? Pi j, so P in pi j. Then you take all functions which have integral 0 on these partitions. This is a subspace, and it's easy to find the codimension, which is the cardinality of the this partition. Is this clear? You have a smooth function. It's supposed to be 0 integral over the small partition elements. If you have, let's say, little bump functions which are positives, then you can find the codimension of the space by adding these functions appropriately. So it's an easy proof. If you have the codimension and you now, there's a general idea using the min-max principle, the counting function with respect to x can be broken down to the sum of the partial answers plus the cardinality of the codimension. Now if you make x, choose x appropriate such that there will be no first eigenfunction, then this sum will be 0 and the upper bound is just the cardinality. Just min-max principle and easy linear algebra. And the fact that you can find nice functions which are positive on these elements. So that's the first part. The lower bound is a bit more involved, and I will be a big wake here. So we now the inequality sign changes. Now it's bigger. It's not it's a partition, but here we take only elements of the same size. So it's a real restriction, but I do it with different exponents alpha. Now I ask the same question: what is the rate, how this increases? This has very much to do with what people call the coarse multifractal formalism. So the number which comes out is called the coarse multifractal dimension with respect to alpha. But what we do in one step further, because we are not interested in this alpha actually, but we are interested in how this quotient behaves compared to the x. And the x is 2 to the minus alpha n. And so if I take the logarithm, then the alpha comes down. So now I'm making this optimal by taking the supremum over this lim sub and lim inf over alpha. And then we call this value f upper bar and capital F lower bar. And this turns out, under the assumption, again, now expressed in terms of j, you have this the inequality turned around, and we don't want this for any function. We are saying there exists, for each q there exists the function psi q, such that we have this inequality with the same j. Then we get a lower bound in terms of this f. And now we want to get this upper bound and lower bound together. What we need to do there is to find the partition function, which is, in the case that j is a measure nu, well known, because then you have the measure of a cube of the generation n to the q, logarithm divided by the size, which is called the RQ spectrum for people from fractal geometry. So this is a generalization of the RQ spectrum and has nothing to do with the spectral problem, because now it has some nice properties. If, oh, there's something strange here. If j would be the measure nu, then the value in 0 is the upper box counting dimension of the measure nu, defined in this way. If it's nu, it's called the RQ spectrum, and this function, if this infinity dimension of j is finite, so then there will be an intersection, positive and finite, then there will be an intersection. This function actually of q is decreasing and convex. And it's positive in 0 typically, and that will have a unique 0, and this will be called Qn sub j. And it's the infimum of all Q's such that this sum is finite. And this reminds you maybe of ideas from Poincaré series, where you use exactly such a sum to determine the Hausdorff dimension of the limit set, the conical limit set of a Kleinian group. I give an example here for the Sierpinski tetraeder in Rd with some probability vectors. We don't have to look at the rest. We come back to this picture once more. So this is it's a typical picture. The dimension, the Minkowski dimension nu will be 2 in this case. It's a convex function. It has a unique intersection, and to the dotted lines we come later, because this gives natural upper and lower bounds for the Qn, because the Qn plays now the most important role. Some more observations from this picture. The asymptotic direction of this convex function is minus the infinity dimension. It will be strictly greater than minus infinity. In 0, it cannot be greater than d, so that it's bounded above. And the question, is there a difference between tau d and tau n, which I didn't focus on, I think. Because here's a slight difference. Here I don't take, if I take d, I don't take all cubes. I leave out all cubes that intersect the boundary. This has to do with the Dirichlet problem, because there, you need some space to get the functions down to 0. And so does this make a difference for this function? And the answer is given here, at least if the support of j, so it takes the intersection of all j's, all q's where j is positive, if this is strictly inside the interior of q, then there's no difference, which is immediately clear, but also for other examples there's no difference. It's scale invariant, so if you multiply j with some constant, then it doesn't change. So a bounded or probability measure doesn't make a difference. That's what it says. So in the next step, we want to connect the problem we had before to this number qj. And for this, we have to construct an optimal partition which we needed for the upper bound. And this is done by taking all elements in the dyadic setting, which are just below t for a given t. So if you go one step up, so it's contained in another cube, if then it's greater or equal to t, then we have to go one step further, and then we take this interval. This gives a partition, and it has only to do with j and nothing with the spectral problem. The cardinality, how this increases, lies below qj of n, and hence gives also an upper bound for the h up j, which was the, what would I call it, the upper partition entropy. So we get a new upper bound in terms of q, which is an easy to handle parameter. And because this proof is, one should give one proof, and this is so easy, I decided to give this proof, because if you go back, so here's just the elements which drop just below. And if you take the partition of all q which are greater than t, then there is an easy connection. The cardinality is less than 2 to the d times this cardinality, because for each there are at most 2 to the d subintervals. And now we want 2 t to q, the cardinality of pt, you write it as a sum over ones. Then because you have this inequality with the t, we can rewrite t to the q. No, first we go from the partition pt to rt, and we get this factor 2d. And now we can use t to the q and know that this is smaller than jq to the q. And now we have this complete sum over all cylinders. And if the q is chosen, the t is chosen such, no, the q is chosen such a way that this is finite, then also this side is finite. And so we know that for q greater than qj, this is finite, and this gives us immediately the inequality, because this partition is one particular partition, and for h, we take the infimum over all partitions, so it's also even less than this one, and we are done. Okay. Now the point is that also for the lower bound, for the upper, so the lower bound is given by f, and the lim sub was denoted by f upper bar, is equal to qj. And for this, we need refined large deviation arguments. So where you normally have nice tools from thermodynamics, here you need really dirty work on, say, probability theory. And you use large deviation theory for this kind of random variable. It's fun if you like it. But this gives you this nice formula, because now you know the S upper bar we are interested in is bounded between F upper bar and H upper bar, which is bounded by Qj, so they're all the same. That's what I mean with a complete answer to a partial question. So for the upper spectral dimension, I have a complete answer. We come to that when we look at the main result. In other cases, there might be a chance that you not only have this intersection point, you have the whole graph. So if this graph has some nice regularity properties, this is typical for large deviation, like the first one is at a critical point qj, the limit, so it's defined by a lim sub, the limit exists on a little strip left to this point. If this is true, or if at this point the limit exists and it's differentiable, so either of them or both, then we know that also for the lower bound it's equal, and so they must all be equal. So this regularity condition on the function tau, which has all the information we need, if this is fulfilled, then we can give a complete answer to the upper and lower spectral dimension, at least for the Neumann problem. So how do we connect now these general results for the J with this concrete problem? And here comes a nice result by Mathia. This was used already in this first paper I mentioned, where they showed there's a compact embedding if and only if. If it's greater than d minus 2. Actually, what Mathia and Adams showed first, this embedding constant can be made optimal with respect to this problem if we choose it for, as this number. So here you have a supremum over all sub. So d of q means q is some cube, and d of q is the set of all subcubes of q. Takes the supremum over these numbers with some a and b, and if you choose a 1 over d minus 1/2 and b 1 over t, then there will be a compact embedding into LT, where t must be greater than 2. So there's a little problem, because we want this for t equal to 2, and this only holds for t greater than 2. This doesn't spoil the upper bound, but this spoils the lower bound, actually. And the case that's also not so nice, the case d equals 2 has to be treated separately with this bound, log of the cube to the 1/2 and times the new measure. So we have a function j which connects the Lebesgue measure and the measure nu in a very complicated way. And if we take this as our function j for a given t, then this will solve the problem, because then we can apply the theorem from above. We do have this embedding constant. We do have the same constant for the lower bound. We have to construct a function using smoothing methods, these modifiers. I'm not an expert in this, but it works. And then you can apply all this to get first an example. So the good thing is, so this depends on J nu, and J nu is very complicated because it's a mixture, it's a supremum over all these products. if you have a nice situation like an absolutely continuous measure, or the alpha regular measure, or, and this is new, a self-conformal measure with arbitrary overlap whatsoever, then this function is given by the LQ spectrum plus a linear function. And so this is the connection. We proved that the tau nu is equal to the sum, and Solomjak and Paris proved 2000 for a little different case for self-similar measures that the LQ spectrum always exists in that situation, no matter what kind of overlap you have. So this was a nice observation from which we could use. Otherwise, we would have got stuck there because we need this regularity to go to the end and show what the dimension is. So now we come to the main theorem. If always under the assumption that the infinity dimension is greater than d minus 2, we have the equality of the upper dimension with this number q to the n. So this is for the Neumann. Dirichlet is a problem because we do have an upper bound only in terms of Neumann. So we can only solve the Dirichlet case if we know that fd lower bar is equal to qn. Otherwise, we are stuck there. But for the nice examples, this works. Because so for that, you need that these two functions, tau d and tau n, coincide, and then you also have the Dirichlet case. For dimension d equals 2, the upper spectral dimension is always equal to 1. So coming back in a second to the Kutch question, do you hear the shape of a drum? Not in dimension 2 often, obviously. So you shouldn't play a two-dimensional drum in this sense. So now the proofs gets very short because we have done all the complicated work. We use the optimal embedding constant. We combine this with our observations from these from the speed of convergence of these increasing sets, and this gives you the equality. And we have this equality, and then we are done. And for the lower bound, you also need the min-max principle and the modifier method. And you have to prove that for certain functions q, you can find a case such as this holds for all q, no matter how small they are. The problem was this Martial theorem was not for cubes, it was for Rn, or for Rd. So you need some methods of restriction operators and show that this does not depend on the size of the cube, but only on the shape. And actually, if you have Lipschitz boundaries, and so it's a scaled copy of a Lipschitz domain, then you are fine. Lipschitz domains means that the boundary is can be written as a Lipschitz function with finitely many pieces. All right. Now, the regularity conditions can be read off now if you have that the function is partition function regular. So you have this either differentiable in this critical point, or it exists as a limit to the left, then the dimension exists. And this is also true for the point QD. So that means QD and QN coincide, then the two spectral dimensions for D and N coincide. So Dirichlet still makes some problems, so we don't have the complete picture here. And now coming back to our examples, because we have seen how these functions look like, so for the case of absolutely continuous, they go through D, have a certain slope, like -2, and the intersection point is d over 2. We immediately have this problem settled. For the case alpha, so here we have d minus 2. We have alpha in between, and then we have a slope alpha. Then this number, this intersection point, is just this alpha times alpha d minus 2. And for the self-conformal measures without any separation condition, we know that this limit exists, and it's so we have either we look at this tau j, but this is equal to beta nu plus this linear term. So actually, if you look at the LQ spectrum, and then you look at a line with slope d minus 2, there must be an intersection point, and this is actually the QM. So you can read off the upper spectral dimension from the LQ spectrum. So that's what I would call the geometric information in this setting is completely stored in the LQ spectrum. Now it gets complicated. Now, so more examples. We've easily constructed an example in one dimension where the spectral dimension does not exist. Just construct an example where the Minkowski dimension does not exist, and then you put out some mass, and this works just the same. To catch question, how is this now related to the intrinsic geometric information or measured geometric information? Well, we have these bounds in dimension d greater than 2. We have a lower bound given by the Minkowski dimension in this way for Sn, and we have an upper bound in terms of this infinity dimension. So there is a connection to geometry, but it's maybe not that strong as one would expect it. The proof of that is just because it's a convex function. In the point 1, it must be greater than d minus 2. And this gives you that this connecting line, this dashed line, must lie underneath the convex function. And then this intersection point gives you the lower bound. And for the upper bound, you use the asymptotic direction, goes through the same point, and this gives you an upper bound. So it's really just convex analysis to get these two bounds. In dimension 1, it's the other way around. You get an upper bound in terms of the Minkowski dimension. So it's always less than 1/2. This was known years ago. Now it's actually less than box counting dimension over 1 plus box counting dimension. And you can give a lower bound in terms of the upper and lower derivative in the point 1. So in dimension 1, things are much easier. Actually, the whole embedding problem is gone because you have a compact embedding in continuous functions. You have the LQ spectrum. You look at the line with slope 1, and this intersection point is Qn. And of course, this line, so this is 1, there must be 0. So this line lies always above. And if you have the slope at this point from the left, gives you always a lower bound. So it's quite easy to read off geometric information from this picture. And in particular, if it's differentiable in beta nu in 1, then you know that the Hausdorff dimension of the measure is in between the left and the right partial derivatives from the right and the left. So the directional derivatives. So the Pecking and Hausdorff dimension of the measure are equal and are lower bound for these spectral objects, the lower and the upper. And this is less than the Minkowski dimension. So whenever you have an example where the Hausdorff dimension and the Minkowski dimension of the measure coincide, then you know that the spectral dimension must exist. These are, in particular, the alphas regular measures. And okay, in dimension 2, now things are a bit annoying because here the only outcome is 1 for the upper dimension. If you assume that it's differentiable, so there will always be a 0 in 1. So this is the Qn will always be 1. If it's differentiable there, then you know everything is equal and the spectral dimension is 1. So there's all the information is lost somehow. And if you have some extra information, There's some misprints. Here it should be just for the Neumann problem. And if you have extra information that the support is inside the cube, then you can say the same thing for the Dirichlet problem. So you have to be a bit careful. And then we have a rigidity result in the sense when this function somehow is maximal, because we know it's convex, it must lie above a certain point. If it attains this maximal value at one point, being convex, it must be a straight line. And then we know also the value of S. So and the other way around, if you know the value of S is equal d over 2, this is a minimal value for d greater than 2 to be attained, then the tau spectrum must be a straight line on this bit. And the other way around, if the 2n exists as a limit and equals d minus 2k, so it's slope minus 2 and fits exactly, yeah, we come to an end very soon. And then it must be a linear function, and you know that the upper spectral dimension must be d over 2. And okay, I have some extra material, very rough. So the critical case can be dealt with. So there's an absolutely continuous measure, which is supported in such a way that this has a singularity in this point. Depending on how strong the singularity is, you either have no continuous embedding, you have continuous embedding but not compact or compact. So everything can happen. And then in the compact case, it's equal to, and now we come to the extra material, and we can skip that if you like, because in dimension d greater than 1, this condition that d infinity must be greater than d minus 2 excludes the possibility of having atoms. This is not true for d equals 1, and that's how we started actually with to look at purely atomic measures with certain atoms and certain weights, and try to prove how this connects to the Minkowski dimension, and in fact it does. And we found example that the atoms are in the way that you have a behavior like the Lebesgue. You have trivial behavior, so it's 0 all the time, or you have some scaling. So you choose the particular sequence kx, k plus 1 to the minus u2, and for the weights you choose something like n to the u. Then we know how this function looks like. It's linear, and we immediately can calculate the spectral dimension. And dimension 1, Dirichlet and Neumann are always the same. That's why I left off the d and n. And if you take the particular choice u1 is equal to u2 plus 1, then the spectral dimension is actually half the Minkowski dimension. So then you have Kutsch's question positively answered. And that was all I wanted to say. Thanks for your attention.